Hi friends, welcome to our channel. Let's have a look at problem 3599, partition array to minimize exclusive OR. Here in this video, we are going to practice dynamic programming. Let me write some notes here. So the technique here will be dynamic programming. So here I'm going to present two formats. One is tabulation, the other is in recursion format. So we are going to follow the hints given in this problem. So first, let's look at the problem statement, which is very short. So we are given an integer array called nums and an integer key. So we want to partition the nums into key non-empty subarrays. So because of this partition is not unique, right? So after you get a partition, you are going to compute the exclusive OR for each subarray within this partition. Then you get the maximum, right? Then based on different partitions, you get different maximums. You want to find the minimum among these maximums, right? So that's the problem requirement. So if you look at the three examples given, so especially if you look at example 2, this actually is a bit more general than example 1 because here's k is 3. For k equals 2, so you can try this is the one subarray and this is the other. This is the one partition. And then the first subarray can contain 2 elements. Then the 3 contains another. There are only 2 partitions, right? So you can verify the explanation. So similar you can do for example 2, but it needs some more partitions. So here the length of this nums is bounded above by 250, right? The length is not very large. And here this is the range of the elements, positive numbers in particular. So here k is bounded above by n. So in other words, so if you want to use a table, so for example, the table is roughly bounded above. Table size is roughly the length, let's call it n, right? N square, roughly like this, right? So you can choose n plus 1, that will be n plus 1 square. So that's the size estimate. So this constraints actually give the problem size upper bound, right? So now we're going to look at the hints. So we're going to use dynamic programming. So actually these hints are very very to the point. If you follow the hint, you should be able to get a solution. Then the thing is, how do we implement this? So in the first version, I'm going to use a tabulation. So here first, I'm going to get the length of this nums. So this is just for convenience. And then I'm going to compute the exclusive OR for the first I element. Compute exclusive OR result for the first I elements. So this can be very easy, right? So you can use pre. So for example, the first 0 element, you get the result is 0. And then basically for I in range n, right? So we are going to consider the current element. So if you consider I, so then the number element will be I plus 1, right? So I'm going to append to this one. So then let's see, exclusive OR so far. Let me add more variables so that we know what we are doing. So this will be pre the last one here, right? This currently 0. Then exclusive OR with nums I, right? So what we are going to do is to append the exclusive OR so far, right? So this way, if you call pre-I, so this will be the exclusive OR result for the first I elements. So we can print out this. Let's use example 1 to examine that, right? So the 0th element, first 0, so you get 0. The 1, so you get 1. The first 2, 1 and 2. So let's see, 1 and 2, you are going to get 1. The reason is, so the exclusive OR of 1 and 2 it's nothing but 0 1 exclusive all with 1 1 0. So this gives you 3, right? So 1 1, that is 3. So in decimal, right? This is in binary, right? So let's see. You get 1 and 3, and then the last one is 3. 3 exclusive all with itself. You are going to get 0. So everything is right. So now let's look at our DP. So here I'm going to use this one, and DPIG. It will be the corresponding result, that is the minimum possible maximum exclusive all among this result for when splitting I elements, the first I elements, into G parts. So here parts means G subarrays, right? So with that done, let me first initialize that. So here I'm going to use float infinity, right? So here you can choose to partition the first element into 0, 1, or 2, right? So 0 is just a dummy, right? So here we write k plus 1. And then for a dummy index, so here, let's see, I guess I should put this bracket here. So for I, for the dummy index in range, so I will write also m plus 1, right? So then the dp0 0 should be initialized as 0, and this is our initialization. Now let's look at this dp update. This is very crucial and also the core part. So first, for I in range, so 1 to m plus 1. So this is a number of elements, right? So here I interpret as the number of elements. And then for G in range, so this will be the number of partitions, so at least 1, at most k plus 1 in here, right? So here you can interpret G, the number of subarrays. So now we want to determine dpij. In other words, if we want to use the first I items, and then we want to partition them to be G subarrays, what's the result? So here first, because we are going to compute the mean, right? So let's mean of maximum or result of those among a partition among all the things. So it's going to be float infinity, right? And then we want to consider how to add one more, right, from the previous one. So in other words, from so let me first write it down. So because the previous one, so we should consider partition some previous elements into J-1 partition subarrays, and then from that index to the current elements, we form a new subarray that is J1, right? So basically, for n previous elements in range, so it should be at least J-1, right? And then up to this I. So here it should be ending at before this. So here n previous, so the number of elements for J-1 subarrays, right? So because of this, it should at least J-1, because each subarray should be not empty, right? So, and then what we are going to do? So then so the elements, the first J-1 elements is used. Then from J's elements, the first impress, let's see right here, first impress elements are in the first J-1 subarrays. Then the element counts the in previous plus 1 elements to s elements. So here the indexing is 1, right? Should form the last subarray. So here let me write like this, and then what do we do? So the current exclusive OR result is from the this elements to here, right? The result should be the first I element, and then exclusive OR with pre up to this in previous, right? So we use the cancellation property. So this actually is nothing but the exclusive OR result from the in previous plus 1 element to the s element. Notice that here we are using one index because we count the numbers. So this is an important detail to understand. So once you have this, also we know the max of the previous exclusive OR. That would be dp, the mean of the dp in previous g minus 1, right? So then the mean of max of all should be this: mean of the current state, mean of max exclusive all, and so the previous partition, right? So this one, the max of previous exclusive all and the current exclusive all, because this corresponding to one partition the in previous one with to g minus 1 subarrays. So from this part corresponding to the last subarray, in total we want to find the maximum, right? So this will be the mean of the previous maximum corresponding to one partition, right? And you can see this, that is the corresponding, though it's interpreted as mean, it should be the maximum corresponding to that special partition. Let's call it P0, right? So this subarray, so basically from this nums, let's see, in previous, right, up to g minus 1, I would say, right? So this subarray and plus this P0 forms a new one, because this one is a corresponding maximum corresponding to P0, and then if you compute maximum with respect to this one, this is the best partition corresponding to the thing, right? So you get the max. So this forms a partition of the whole thing up to I corresponding to P0 with the first in previous elements. Notice that we need to iterate for all possible in previous, right? So in other words, this is a rigorous or correct logic. So once we have this, then after this for loop, so we get the information for dpij. It should be the mean of maximum all. So now once we have this, so we should be able to return the result. What we want to return, we want to partition n element into key subarrays. Let me first run it. Yeah, it passes all the cases. So now let me submit, and then we make some comments and prints. It's running slow. I don't know what's the problem. Hopefully it will pass all the tests. Okay, it passes all the cases. So let me print out something so that we can better understand the logic. Print out dp. So let's see. Let's see for the first example. For example, if you partition 0 elements into 0 partitions, you get 0. You partition 0 elements into 1 as you get infinity, right? It's impossible. If partition 2 is impossible. This is the first line corresponding to example 1. And then if you partition one element into 0, that's the infinity. If you partition one element into 1, it's just itself, just 1. So this is the 1. If you partition one element into 2, it's impossible. You get infinity. So now let's look at the first two elements. So if you partition 2 elements into 0, you get infinity. If you partition 2 elements into 1, so that's the exclusive OR of 1 and 2. So that will be 3, right? You get 3. And then if you partition 2 elements into 2, so the max among these two will be 2. You get 2 here. So now let's look at last. If you partition 3 elements into 0, you get infinity. A partition into 1, so all the elements. So 1, 2 have exclusive OR result 3. And the 3 exclusive OR with itself, you get 0. That's this one. And then if you partition 3 elements into 2, right? So there are two possibilities. You can first partition the 2 elements into 1 and add this one. So partition 2 elements into 1, you get 2 elements into, let's see, 2 elements into 1, you get 3. 3, and currently you have 3. So maximum will be 3, right? And then you can also partition 1 element into 1. So 1 element, you get 1. So 1, 2, and 3, the exclusive OR result will be, let's see, 2 and 3. You get 1, 0. Exclude OR with 3, you get 0, 1. That is 1. Anyway, you also get 1. The larger of 1 and 1 is 1. You get this one. That's the last result, right? So this is the first example. So now if you look at the second example, right, you can similarly interpret. So now let's directly look at the last line. So if we partition 4 elements into 0, you get infinity. It's impossible. You partition 4 elements into 1. So that's a whole array. Because in this array, you have 2 2s and 2 3s. They cancels. So you get 0. So now if you partition 3 elements, 4 elements into 2, right? So 4 elements into 2. So you can consider partition 3 elements into 1 and then compare with this 2. So the 2 and 2, the minimum is 2. This is not the 1. Now also you can consider partition 2 elements. Let's see, 3 elements into 2, you get 2. 2 and this 2, you get 2, right? And then you partition 2 elements into either 2 or 1. Let's partition it into 2. You get 3. 3 with respect to this 2, you get the maximum is 3. And then if you partition the first 3 elements into 1, you get 1. And 1 with respect to this 2, you get the smaller. The maximum is also 2. So then you can also see this one. Let me see. Let me directly get this one. So let's consider example 2. See, 4 elements. Let's see. What we are looking at is 4 element 2, right? Into 2 subarrays. So you can consider first 3 elements into 1, and you get the last element, that is 2. So the result is this, and 2 3s, they cancel, you have 2. So 2 and 2. This is the exclusive OR result. So the maximum is 2. And also you can consider the first 2 elements into 1. And then you get 2 3. And then the last element should be this one. So you get say 2, 3 is 1, 0 and 1, 1. You get 1. So in other words, so the corresponding XOR result will be 1, 1. You get 1. So this is actually exactly this one. Or you can also 1 elements into 1. So that is the partition will be 2 and 3, 3, 2. So the exclusive OR result, the first one gives you 2. The second one also gives you 2 because the 2, 3 cancels, you get 2. So the maximum is 2. So then in this one, this position, it should be 1. So now let's look at the last one. So 4 elements into 3 subarrays. So this is what we want, right? So then the first 3 elements into 2, and then the last one has 1. That is this. The last element is 2, right? So then the first 3 elements into 2. So the result is 2. So you get 2 and 2 exclusive ORs. So you get 2. Then also you can do 2 elements into 2, and then the last one will be 3 and 2. So now the 2 elements into 2, the 0, 1, 2. 2 elements into 2, you get 3, right? And then now you have 3 and 2. So 3 and 2 gives you 1, but the maximum of 1 and 3 is 3. So this gives you 3. So the minimum of 2 and 3 is going to have 2. So min of 2 and 3. So you're going to get 2. So this is exactly this position, right? This is also the return. So I guess with this print, you should be able to know the details of the dynamic programming. So this is one way to do the problem. I guess so far, because we explained the details for the DP table, it takes longer. So I'm going to stop here, and in a follow-up video, I'm going to do a dynamic programming using recursion, right? So with that said, that's it for the current solution format. Thank you for watching.